Further trigonometric identity is a double angle formula. So we've already seen that sine A plus B is sine A cos B plus cos A sine B. So if we replace a B with A, we get sine A plus A is sine A cos A plus cos A sine A. Or if we simplify that, sine 2A is 2 sine A cos A. So sine 2A is 2 sine A cos A is a double angle formula. So if we divide by 2, a half sine 2A is sine A cos A. If we double the angle, 2A to 4A, then we get sine 4A is 2 sine 2A cos 2A. If we times everything by 3, 3 sine 2A is 6 sine A cos A. And if 2A is 60 degrees, then sine 60 is 2 sine 30 cos 30. Similarly, cos A plus B, cos A plus A is cos A minus sine A. So simplifying that, cos 2A is cos squared A minus sine squared A. There's another double angle formula. We can replace cos squared A with 1 minus sine squared A to get 1 minus sine squared minus sine squared, or cos 2A is 1 minus 2 sine squared A. Or we could replace sine squared A with 1 minus cos squared A to get cos squared A minus 1 minus cos squared A, or 2 cos squared A minus 1. There's 2 more double angle formula. So you can see there's quite a lot of these double angle formulas we need to know and be aware of, although we can work them out from the addition rule from earlier. Tan A plus B, same idea, replace the B with an A. Tan A plus A is tan A plus tan A over 1 minus tan A, which is 2 tan A minus over 1 minus tan squared A. So a half tan 2A is tan A over 1 minus tan squared A. If 2A was 60, then it'd be 2 tan 30 over 1 minus tan squared 30. If we times it by 2, 2 tan 2A is 4 tan A over 1 minus tan squared A. And if 2A is equal to A, then tan A is 2 tan A over 2 divided by 1 minus tan squared A over 2. So there's the double angle formula for tan. So we can use these to do all sorts of exciting sums. 2 sine theta over 2 cos theta over 2 cos theta. We want to rewrite it as a single function. Well, we sort of recognise a bit of it. We say, hang on, there's a 2 sine cos. That looks like a double angle formula. But it's theta over 2, so that means that the 2 theta bit must be theta, so I get my theta over 2 in the thing. So sine theta is 2 sine theta over 2 cos theta over 2. So I could replace that 2 sine theta over 2 cos theta over 2 with just sine theta. There we go, the blue lines showed a bit I'm replacing, so I'm left with sine theta cos theta. That, however, isn't quite a single trig function, so we can rewrite that as a half sine 2 theta, because if we look at the thing underlined in blue we can see the similarity between them, and now we have done it. Show that 1 plus cos 4 theta can be written as 2 cos squared 2 theta. These are common exam questions to show that one, so we have to be able to show enough lines of working out to convince the examiner that we know what we're doing. So let's use a double angle formula. Cos 2 theta is 2 cos squared theta minus 1. Double the angle part now, so cos 4 theta is 2 cos squared 2 theta minus 1. So 1 plus cos 4 theta is 1 plus 2 cos squared theta minus 1, which the 1's cancel off, so you're left with 2 cos squared 2 theta. Given that, cos x is 3/4 and x is between 180 and 360, find the exact value of sine 2x. Triangle time, adjacent hypotenuse, Pythagoras, to find the missing side. Remember to ignore any negatives, not that we have any in this case, so it's root 7. So therefore sine opposite hypotenuse, root 7/4. Cosine x is positive in the range 270 to 360. So therefore sine x is negative. So sine x minus root 7/4. Now, using the double angle formula, sine 2x is the same as 2 sine x cos x. Sub in the values we've just calculated, 3/4 and minus root 7/4. Work it out, leave it in third form, 3 root 7/8 minus 3 root 7/8. So we've seen this method a number of times now for finding sine, cos or tan by drawing a triangle and using the idea of the shapes of the graphs. This is an extension of the same idea. Value of tan 2x, given that cos x is 3/4. Again, draw a triangle, find the missing side, tan opposite over adjacent. Cos x is positive in the range 270 to 360. So therefore tan x is negative in that range. So tan x is minus root 7/3. So tan 2x, using the double angle formula, tan 2x over 1 minus tan squared x. Sub in the values, evaluate, leave in third form, minus 3 over root 7. Prove the identity tan 2 theta is 2 over cot theta minus tan theta. Well, tan 2 theta is 2 tan theta over 1 minus tan squared theta, using the double angle formula. If we divide each part by tan theta, this is mainly to get 2 on the top, but we will see how it will work out. We've got 2 tan theta over tan theta, 1 over tan theta, that obviously we now recognise as cot theta, and tan squared theta over tan theta, where it'll cancel. So it's 2 over cot theta minus tan theta. Job done. By expanding sine 2a plus a, show that sine 3a is 3 sine a minus 4 sine cubed a. Addition rule. Replace a and b, 2a and a, so it's sine 2a cos a plus cos 2a sine a. Replace sine 2a and cos 2a with the double angle formulas. 2 sine a cos a, and 1 minus sine squared 2a sine a. Times out the brackets. Replace cos squared a. We don't want any causes in our final answer. Often in an exam, this will be worth a mark. As soon as you get to the point where you've successfully got it all in terms of sine something or another, that's often where a mark crops up in the exam. So instead of cos squared a, 1 minus sine squared a. Now it's just a case of multiplying out and tidying up. Group the like terms. There they are, underlined and double underlined. 3 sine a minus 4 sine cubed a, as required. These sorts of questions, very common in C3. To show that, prove that, you have to make sure that all the lines they're working out are there, so the examiner can follow it and not have to guess. As an examiner, I don't like to have to guess what the student was doing. I like the students to make clear what they're doing. Given that x is 3 sine theta and y is 3 minus 4 cos 2 theta, eliminate theta and express y in terms of x. So we've got x is 3 sine theta. If we divide that, x over 3 is sine theta. Y is 3 minus 4 cos 2 theta. Well, subtract the 3, divide by 4 and times by minus 1. We get cos 2 theta is 3 minus y over 4. We also know that cos 2 theta is 1 minus 2 sine squared theta. So if we replace cos 2 theta and sine theta, then cos 2 theta is 3 minus y over 4, and sine squared theta is x over 3 squared. Now we can multiply it out, rearrange it, times by the 4, subtract the 3, and finally times by minus 1, and there we go. Job done again. Solve the following equation in the range stated. 3 cos 2x minus cos x plus 2 is equal to 0. Now we can't solve that because we've got 2x's and x is the angle, so we need all the angles to be the same thing. So we need it all in terms of x rather than 2x. However, we do know the double angle formulas, so we can replace cos 2x with 2 cos squared x minus 1. Now if we times it to bracket and rearrange, we just end up with a nice little quadratic. That factorises nicely. So cos x is either minus a third or a half. Solve both parts. Inverse cos of a minus a third, 109.5. Use the cos graph to find the answers in the range 0 to 360. So 250.5 by symmetry is another one. Inverse cos of a half is 60, and again using the cos graph to find the answers in the range 300. So 60, 109.5, 250.5, 300 are the solutions for x.